A couple of sessions ago, I asked you to write as a group a question or two or three that you still had about Chapter 14 after looking through the learning outcomes for Chapter 14. And I looked through them and found that there were 4 things that came up over and over again. And I'm going to go through those 4 things in this video. So the first one was, what does heterogeneous equilibrium mean? And that I feel like is just a vocabulary thing that I forgot to mention when I was going through the slides the first time. So that'll be relatively quick, but lots of people had that question. Some people wanted to know what I meant by telling a story about what was happening before or at equilibrium. Telling a molecular level story, I think, is what the wording said. A lot of people wanted to know about how you use graphical data to find delta H and delta S from equilibrium data. And then finally, a lot of you are still having are still a little bit stuck on Le Chatelier's principle. So I'll take my best stab at explaining that with a new angle. So first, let's talk about heterogeneous equilibrium. So heterogeneous just means that it involves more than one different phase. And for our purposes, most will involve a pure solid or liquid. So by phase, I mean aqueous, solid, liquid, gas. So if you look at the reaction below, this reaction right here, it has 3 gases and 1 solid. And that is a heterogeneous reaction because it has more than one phase represented. If this carbon were a gas, then it would be a homogeneous reaction. But it's heterogeneous because this is solid. And really, all I want you to know about heterogeneous equilibria is that when you encounter a pure solid or liquid in the reaction, you leave it out of the equilibrium constant. So the equilibrium expression, constant expression for this would be either concentrations or pressures of CO and H2 over the concentration or pressure of H2O, because those are the gases. Those have changeable concentrations and pressures. We leave carbon out because it is a solid and doesn't change in its concentration or pressure, and so that concentration or pressure is factored into the constant itself, and so it should not be in the equilibrium constant expression. So that's heterogeneous reactions. The second one, oops, this is formatted weird, let me change that real quick, is what do I mean by when I ask you to tell a molecular level story about a reaction at equilibrium. This was an activity that I had you do on exit slips early on in the quarter, where I gave you a particular reaction and I asked you to take the role of a molecule and what would you experience. Basically, what I'm looking for there is that you are able to relate the symbolic expressions for equilibrium to what is actually going on in the flask on the molecular level. So when I'm asking you to tell a molecular level story, I want to know what are happening to the molecules themselves, not just that the concentrations in a particular configuration are constant. I want to know more than that. I want to know what the molecules are doing. So here are the criteria I would look for. I would look to see that it actually describes what the molecules are doing, so that it's really important to relate these things to what's actually going on in the flask or beaker. And sometimes the way that I try to get you to do that is by saying, what would you experience if you were such and such a molecule, which is kind of weird, I know, but it works for me. Another way to think about it is, what would you be able to see if you were actually able to watch a video of this reaction? So that's another way to ask. You really want to go to the small particle level and discuss molecules. You also, for this particular type of story, if it's a story about equilibrium, I want to know the dynamic nature of equilibrium. I want to know that the reactions are still going on at equilibrium. And that is a a big reason why I would ask you to tell a molecular level story about equilibrium in the first place, because you don't see that dynamic nature if you're only looking at the equilibrium expression or only looking at the reaction. You would only see it if you were able to see the reaction itself. And so I want to know that if you're looking at a molecule of the reactant and the reaction is at equilibrium, that every once in a while that molecule of reactant would probably turn into a molecule of the product. And then at the same time that that happens, if it's at equilibrium, a molecule of the product would turn back into a molecule of the reactant if it's a 1-to-1 stoichiometric ratio. So that's kind of what I'm asking for there. This third bullet point, that the story must discuss the rates and probability, or the rates or probabilities of the forward and backwards reactions happening. Well, that piece is about whether or not the reaction is at equilibrium and how the reaction looks different before and at equilibrium. So before it reaches equilibrium, then the forward reaction would be a lot more probable because you have mostly reactants, if not all reactants. And so the forward reaction would happen at a high rate. If you were a reactant molecule, you would probably expect to be transformed into product at, somewhere down the line. But if it's at equilibrium, then the rates or probabilities of the forward and backward reactions are the same. So every once in a while, you could expect to be changed into something on the other side of the reaction, but then something else is going to change to be on the opposite side, so it maintains that equilibrium. One more thing that I'm going to add here that I forgot when I first made these slides is that the story should connect to the value for K if I give it to you. So that means that if the value of K is really high, then at equilibrium, I would see mostly products if I were watching a video of this. And if it's really low, I would see mostly reactants. And still, though, if it's at equilibrium, there's still both reactions going on. They're just going on at equal rates. So that's what I mean by telling a molecular level story. So what I want you to do on your own time is I'm giving you this slide again. This was in your chapter 14 slides, but isn't on the copy of the slides that I gave you. I think I gave you a printout of these that are sample responses to this question about if you were a molecule of methane CH4, what would you experience before and after equilibrium is reached? So here's some sample responses. I will tell you right now that none of them do all four of the things that I just mentioned. So what I would do, I think a good way to prepare for this and a good way to really deepen your understanding of equilibrium is to evaluate these 5 against the 4 criteria I just said, and then maybe pick one to add to. Or revise so that it better meets all 4 of those criteria, and or write your own.